So the screen is visible, right? So I have written lecture 1 NPTEL. So you can see the screen, right? Whatever am I writing? Hello, hello, hello.
Yes, sir, you are audible and the screen is visible.
Okay, so let me begin by introducing myself. So my name is Sachin here, Gaikwad, and I will take problem solving sessions every Saturday from 5 to 7. Okay, so that's one. So let me just write my name here. Okay, so the second thing is that so we are using Google Meet link for this session, and there is a chance that this Google Meet link will expire after 1 hour. So in that case, I will restart the meeting using the same link. So if you get disconnected after 1 hour, including me, so we'll restart the meeting after 1 hour. And if the link let me continues after 1 hour, then we'll just join using the same link. Okay. So we'll just continue using the same link. So let me just put that in chat because I think some people may join late. So if the link gets okay, so I have put that in chat. So I think maybe we can begin. Okay, so here is how we will proceed. So I have prepared some questions and I have also prepared some answers. So I will put the question here. I will write down the question. So I'll let you guys look at the question and think about it for a couple of minutes. And once the 2 minutes are over, we'll start discussing your ideas. And once the ideas are over, I'll give you the solution. Okay, so that's how it will go. So I'll write the question. So let me just a minute. Just a second. Okay, so I'll write the question. So you guys can start thinking about it while I write. So here is a question one. So what we have to do is, so this is a, okay, so show that uh, in any group of two or more people, there exist at least two people with the same number of friends. Okay, so let me explain the question. So there's a group of n people. Okay, so n is either two or more, and then some of the people in that group are friends with each other. So let's say if there are p1, p2 up to pn denotes person 1, person 2, person n, then it might be the case that person 1 is a friend with person 2 is friend with person 5, like this. And okay, and the second thing is that the friendship is mutual in the sense that if P1 is friend with P2, then P2 is automatically friend with P1. Okay. So now what you have to show is that if there's a group of n people, then there exist at least two people in that group which have same number of friends. Okay, same number of friends, not same friends. Okay, so I'll let you guys think about it for a couple of minutes, and if you have any ideas, you can start sharing.
Uh, Hello, sir.
Yes, I can hear you. Yes,
Can I share my idea?
Sure, sure. Yes, yes,
yes, please.
please.
Suppose if you take P1 up to Pn, that is a person basically,
Mhm.
then in that case, with the given conditions, suppose I make the degree sequence, then it
Okay.
will be 0, 1, 2, 3 up to n minus 1 according to this condition. But
Okay.
this is not a degree sequence. We can
Why?
use Hakimi-Havel algorithm, or another idea is that suppose if there is a person
Mhm.
with whose degree is basically n minus 1, then there cannot be a vertex, means a person whose degree is basically 0. So here we
Ah,
will get a contradiction.
Yes,
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 yes, yes.
yes.
So, so your idea is correct. So I'll give the same solution. Okay. So let me repeat what he said. Okay. So what we will do is first we will map this question to a graph theory question. Okay. So how do I do this? So let's map this question to some graph theory question. Okay. So how do we do that is we have to construct some vertices and some edges so that the same question will be converted to some graph theory question. Okay. So the way we to do that is first I will assume, so rather I will denote the people with vertices. Okay. So if there are n people, I will make a vertex p1 for person 1, p2 for person 2, and then pn for person n. So we will take, or rather construct, a graph with n vertices where vertex v1 corresponds to person 1, corresponds to person 1, or I would say person pi corresponds to person pi, and then there are n vertices. So because there are n people, there will be n vertices. Okay. Now, okay, so somebody saying, can you please zoom in the screen? It is only occupying 25%. Uh, okay, actually, let me see. I'm not sure how to do that because I'm using my iPad to present. So let me think. Oh no, I think it is even smaller. But is it too hard to see, or is it this much is fine? Because I'm not sure how to do that. So maybe this time I'll stick to this. The next time, oh, it's too hard to see. Okay, let me. So do any one of you know how to do that, or let me see.
Sir, it's clearly visible for me. Maybe the problem is with that person. He or she can zoom it.
Okay, okay. I think there's an option. So there's a full screen option that will maybe make the screen little bit bigger, but it will still contain only 25 or like whatever you said percentage. But I think you can make a full screen, so that will be little bit better. Okay. So now let me get back to the answer. So like I said, so there are n people. So I'm putting n vertices, one vertex for each person. Now what I will do is the following. Suppose the person I is friend with person J, then in the graph that I'm trying to construct, I will add an edge between the vertex Vi and vertex Vj. Okay. So if person I is friend with person J, Then we will add an vi comma vjh. Okay. So this is how we are constructing graph. Basically, for n people, we are putting n vertices, and sub of the people are friend with some other people. So every time person I is friend with person j, I will add an h vi to vj. Okay, and this is an undirected h. That is, there is no direction because the friendship is mutual. If vi is friend with vj, then vj is friend with vi. So there is just an undirected h. Okay. Now once we have this mapping, what I will do is that re let's reread the question and let's see how what it says in terms of graph theory. So we have to show that in any group of two or more people, there exists at least two people with the same number of friends. Now, can you see that in this newly constructed graph, the number of friends the person I has is exactly the degree of vi. So what I'm saying is degree of vi is equal to number of friends of person I. Can everyone see that? So if you understand the last line, then can you put +1 in the chat so that I will have some confidence to go ahead? Okay, so and if you have any questions, you are free to ask. Okay, there is no. Okay, I see a lot of +1s, at least 4 or 5. Wait, so there's a question in Hamilton. So we'll get back to the questions at the end. So let me first finish what I have prepared, and then I will answer the questions. Okay. Arya Shankar, I will answer it at the end. Okay. So this is it. So what we have is degree of vi is equal to number of friends of person I. Now, if you see, the question is asking every person has different number of friends. So sorry. The question is asking, does there exist at least does there exist two people with same number of friends? What does that mean? The question is asking, is it true that when you construct a graph of that friendship mapping, is it always true that there will exist two vertices which will have same degree, right? It's the same question. So we have to show, so we have to show that in a graph, we will have two vertices. We will have at least two vertices with same number of friends. Sorry, with same degree. Just okay. Okay. So now, so the way we will prove this is by contradiction. So let's assume that there is no such things, that there are no vertices with same degree. Okay. So let's first see what can be the degree of a vertex in a graph with n vertices. Right. So the degree cannot be like n plus 5, right? So if there are n vertices in my graph G, the degree can be at most n minus 1, and it can be at least 0. It cannot be negative. Okay. So the possible degree of a vertex in a graph with n vertices can be, so it will come from this set, right? So it can be 0, 1, 2, up to n minus 1. So every vertex must have a degree which is from this set, a number from this set, like 0, 1, 2, dot, 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 up to n minus 1. Okay. Now, once we know that the degrees are coming from this set, how many vertices are there? So there are n vertices. So there are n vertices. Now, for the sake of contradiction, I'm assuming that there are no two vertices with the same degree. What that means is that every vertex has distinct degree, right? And there are n vertices. And if you see the set which I have written here have exactly n possible values, which means that every vertex have to choose a unique number from this set and that will be the degree of that vertex, right? So uh, every vertex in the graph G must have unique number, or let's say neighbors, from the above set. Now, like I think some he explained, what we have to do basically is that we have to ask, does there exist a graph G such that the degree sequence is exactly 0, 1, 2 up to n minus 1. So now the question is there a graph with degree sequence 0, 1, 2 up to n minus 1, and the graph contains n vertices? Now, there is one simple observation that proves that there is no such graph. So let's prove that. Okay. So if you observe what this graph is, so what we want is one of the vertex must have degree n minus 1. So let's say, so let, without loss of generality, assume that vertex, let's say V, has degree n minus 1, has degree n minus 1. Now, if you observe, there are n vertices, right? And there is a vertex V which has degree n minus 1. This is only possible if V is adjacent to all the vertices in my graph G, right? That's the only way V can have n minus 1 neighbors. Now, if V is adjacent to all the vertices in my graph G, every vertex must have degree at least 1, right? But this is a contradiction because my graph wants a vertex with degree 0, which is not possible. So since there's a vertex with degree n minus 1, there cannot be a vertex with degree 0. Therefore, such a graph does not exist. And since this is a contradiction, what we had assumed before, that there is a graph with there is a graph such that all the vertices have distinct degrees, is not possible. That means there are two vertices with the same degree. Okay. So this is a proof. So if you have understood the proof, then put +1 in the chat. And if not, then ask me questions. I will answer it. So wait. So can we get recording of this problem solving session? So it will be available to you. Uh, I'm not sure when exactly, but I'm sure this recording will be shared with all of you. Okay. Yes. So I see only two +1s. So for the rest of you, if there is any doubt, please ask me. Okay. What that common degree be? I don't understand your question exactly. Oh, so are you asking that the two vertices which had same degree, what is that degree? So this is not necessarily unique. There can be two vertices with the same degree and the degree could be 1, 2, 3, could be anything. It is not necessary that the unique degree must be 1 or n minus 1 or anything like that. Okay. Yes, I hope I have answered your question. Arya Shankar. So, like I said, I will answer the other questions at the end. For now, let's focus on the problem that I am doing. Chances in favor of some degree. Um, Not necessary. So, uh, Okay, so like I said, this is not necessary. You can have a graph with common degree 1, common degree 2, common degree n minus 1, anything. So there is no such question of having only this degree or that degree repetition. Okay, so I hope I have answered your question. Okay, so let me give you second problem. So while I write, you guys can start thinking about it. Okay, so let me just see. Okay, so here's the problem. Okay, I think let me just okay, let me just write down here. Okay, so let me write down. So again, there is one more problem on degree sequence. So the question is that, is there a graph with degree sequence or degrees 3, 3, 3, 3, 3, 5, 5, 6, 6, 6, and 6? Okay, so take a couple of minutes. You can think about the problem, and if you have the answer, please wait for a couple of minutes so others can also think and have some idea. Okay, so meanwhile, I'll ask the problem again. So what we have to do is we have to construct a simple graph, or in this case actually any multigraph is also uh, okay. So can you construct a graph such that the vertices, so will have degree sequence here, this 3 3 3 3 3, then two fives and four sixes. Okay, so take a couple of minutes. I'll wait for you to think. uh, Okay, so I think somebody is writing some idea in the chat. I'll get back to you just a minute. So let others think. So and then we will discuss your idea. Okay. So I think so. Somebody has written in the chat that we cannot have a graph with odd vertices having odd degree. Number of vertices having odd degrees would always be even. And then there's one more. So number of odd vertices must be even. Okay. So I think you have got the idea exactly. So if you remember from your lecture, so you must have seen there's something called handshaking lemma. So let me write it down. So handshaking lemma. It says that the sum of degree of vertices. So let's say if you have n vertices in the graph G, then the sum of degree of all the vertices should be 2 into number of edges. Okay. In other words, the sum of degrees must be even, right? Because like I said, this is the RHS of this equation is 2 into number of edges. Mod e is an integer, a positive integer or zero. Either way, it will be even. So that so the sum of degrees must be. So if you see in the above degree sequence, the sum is not even, right? Because if you see again, I mean, if you add all of them, so this is 3 into 5 plus 5 into 3 plus 6 into 4. This is 15 plus 15. Oh, sorry, this is 5 into 2. This is 10 plus 24. This is 9 4. So if you see the number of, sorry, so the sum of degrees here is becoming 49. Clearly 49 is not an even integer. That means there is no such graph, right? So if you understood this, please put +1. If you have doubts, please ask me. So meanwhile, I'll write the next question. Question. Sir, what does that F denote? Oh, so sorry. So let me go back a little bit. I think there is some confusion. This is E, not F. So this is E, which is 2 into number of edges. So I'm denoting E with number of edges. So I hope that was your question. Okay. Yes, these questions are based on your first week of lectures. So yeah. Okay. So okay. So let's see the next question. So this is again a similar type of question. So where you have given a degree sequence and you have to either construct a graph G with this degree sequence or prove that there is no such graph. You can again take a couple of minutes and think. Okay, so let me see. Does anyone have any idea? Okay, so I think there are some ideas in the chat. So let me read one by one. So first is Arcoil, which he says that not possible because of the same reason, one vertex with degree 5. Um, no, so in the previous question, so this is not a correct argument because in the previous question, what I said is that the number of vertices with odd degree should be even. I didn't say the degree must be 5 or 7 or anything. So if you see here, the number of vertices with odd degree, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 vertices with odd degree, right? So the sum of the degrees of all the vertices is still even. So this is not a correct argument. Okay, so it can be, it is possible that the number of vertices with odd degree is even, but there could be one vertex with degree 5 and another vertex with degree 7 could be there, right? Total number of vertices with odd degree should be even. Okay, so okay, so I think there is someone raising a hand. So if you want to speak, then you can speak, I think. Okay, maybe not. Okay, so the next argument is that no, this time we have even vertices with odd degree. E- that is also fine. You can have even vertices with odd degree. So, for example, here is a graph with so here is a graph with two vertices. Both of them have odd degree, and there are two vertices, and there is a graph, right? So the idea in the previous question was this, and only this, is that sum of degrees of all the vertices should be even, right? In order to have the sum even, we should have the number of vertices with odd degree should be even. Otherwise, the sum will be odd, right? Okay. So there is one more argument. Vertex with 9 degree implies that every vertex with degree 1 and degree 8 will further imply degree with vertex 2. Okay. So I think he is correct. So let me explain. So, so there are how many vertices? 4, 6, 7, 8, 9, 10. So there are 10 vertices. There are 10 vertices. Okay. There is a vertex with degree 9. So there's a vertex with degree 9. What does that mean is that there are 10 vertices and there's a vertex which is of degree 9, which means it is addition to all the vertices, right? So if I start constructing this graph, so let's say this is the vertex u, 2, 3, 4, 5, 6, 7, 8, 9. So let's say this is U0, U1, U2, U3, U4, U5, U6, U7, U8, and U9. So there is a vertex U0, which is addition to 9 vertices, right? That means that every vertex should have degree at least 1, which is true. Right now, every vertex have degree at least 1. But on top of that, there is a vertex which is of degree 8. So there is uh, one vertex with degree 8. So again, without loss of generality, let's assume that U4, so U4 is the vertex which have degree at least 8. Now, if you see U4, I'm assuming this without loss of generality, that U4 is the vertex with degree 8. Now, if you see that since U4 has degree 8, one is U0, right? One neighbor is U0. So U4 is still adjacent to 7 vertices uh, from this U1 to U9, right? So if U4 is addition to 7 vertices, if you can see 1, 2, 3, 4, 5, 6, 7, 8, right? Now, which means that every vertex will have one more degree add in it, right? Before, in the first argument, there was a vertex with 9 neighbors, which was U0, which implied that every vertex have degree at least 1. Now, there is one more vertex with degree 8. That means except for one vertex, U4 is addition to all of them. So let's say U4 is addition to U2, U3, U5, U6, U7, U9, U7, everyone except U1. Okay, it is not addition to U1, which means that every vertex except U1 must have degree at least 2, right? But if you see here in this degree sequence, there is no vertex of so there are two vertices of degree 1, but like I said, there could be at most one vertex of degree 1 and rest of them must have degree at least 2, which is not the case here. So no such graph exists. No such graph exists. Okay, is that clear? If that is clear, then put +1. Otherwise you can ask me questions. Okay. Meanwhile, I'll write the next question. Okay, I think I see +1s. Okay. Okay, so I think somebody didn't understand. So maybe you can ask me if you have any specific doubt in the chat or otherwise. I can answer your specific question. Okay, maybe I'll repeat this argument. Okay, so the question is asking, is there a degree sequence with this numbers written here? Now, the answer is no, because of the following reason. There are 10 vertices in my graph G, right? So there are 10 vertices. This is first observation. There are 10 vertices in my graph G. Now, there's a vertex with degree 9, right? That means there exists a vertex U0, let's say, which is addition to all the vertices in my graph G. So I have drew there's a vertex U0 and it is addition to 9 vertices. That means every vertex has degree at least 1. Okay, I think you are saying you have understood. I think, okay, so maybe I'll move. Okay. Okay. Um, okay. So let's move to the next question. So I hope this is, you can see on the screen. So let me explain. So you have a graph G, and this is a simple graph. That means no multi parallel edges or multi edges and no loops are allowed, right? I hope you remember what is a simple graph. Okay. And then delta G, which is here, is at least K. Now, first, let me explain what is delta G. Here, delta G denotes the minimum degree of G. Okay. That means every vertex in my graph G is adjacent to at least K other vertices, right? So this is delta G, which is the minimum degree of G. Now the question is asking, if I know that my graph is simple and minimum degree is at least K, can you prove that G has a path of length at least K? Okay. I hope the question is clear. So you can again take a couple of minutes and think. And once anyone has any idea, you can let me know. What a path here is. Okay, so I think maybe so let me recall what is a path. So I'll do this by an example. Okay. So this is just a side note, okay, for others can think. So if I have, let's say this is my graph G, and let's say there are some vertices. So this is a simple graph because you can see there are no loops and parallel edges. So in this graph, so A, B, D, E is a path. What do I mean by that? A path is a sequence of vertices. So a sequence of vertices such that consecutive vertices are adjacent and no vertex and edge is repeated. So this is a definition of graph, right? So so what we have is a path, which means you can you can imagine you are standing on some vertex in my graph G and you are moving along. So let's say you went from A to B. So let me draw here. So you went from A to B, then you went from B to D, then you went from D to E. But while you are sort of traveling on this path or on the edges of this graph, you're not allowed to visit any vertex more than once or any edge more than once. Okay. And if that is true, then whatever you have traveled is called a path. So here is a formal definition. Okay. Okay, so understood. Okay. What is the difference between Eulerian train, Hamiltonian train? Okay. I think there are some doubts apart from these questions, but trust me, I will at the end I'll answer all your questions. For now, let's focus on this one. Okay. Taking in vertices and taking view. Sorry. Uh, so, okay. So again, the others can think. Let me just read the chat for a minute. Okay, so there is someone in the chat who has idea. Anybody else has any idea? How can we prove this? Uh, okay, so let me explain the answer. Um, so let me write down a bit below here. So let's say proof. Okay, so there is someone who is saying taking n vertices and taking v1, adjoining it with every vertex n minus 1 will get minimum degree 1, and we will also have a path to v1 with degree 1. So okay, so this argument is not sufficient because it doesn't prove that there's a path of length at least k, right? So let me also tell you what is the length of the path. So in the above example, a b d e, the length of the path is 3, right? Because there are 3 edges. So you travel from a to b to d to e. So the length of path is equal to number of edges in it. So here it will be 3. Okay, so this is the interesting question. So let's prove this. So this is proved using an idea called extremality. Okay, so let me say what is this. So what you can do is this. So let's say let u0 belongs to v of g. So you take a arbitrary vertex v0. Okay, so you have a graph g, right? So there are, let's say, n vertices. N could be anything. I pick a vertex u0 and suppose that a longest path in G with initial vertex u0 has length k. Okay, so let me, sir, not counted scene length. Okay, so there's a question, sir, why you not counted scene length? Okay, so I was giving you an example. Okay, so A, B, D, E is one path. Another example could be A, C, E. So here, see, this is not necessary that path should contain all the vertices, right? Path could be of any length, 1, 2, 3, n minus 1, anything. Okay, that's why I didn't count C, because in this path A, B, D, E, the vertex C is not there. And it is not necessary that all the vertices should be there in the path, right? So let me give one more example of this path in the above this example. So let's say you start with A. So I wrote A. From A, you went to C. So let's say you went to C. So I wrote C. From C, you went to D. So you went to D here. Now, if you see, and I decided to stop, the path is only ACD is, and it is of length 2. Okay, so it is not necessary to. Okay, I think you got it. Okay, so let me rub this. Okay, so let me explain this idea here. So what I did is I arbitrarily pick a vertex u0 from my graph G. Okay, and then what I said is, suppose take a longest path that starts with u0. Okay, it could be anything. u0 is a starting point or a starting vertex, And then I started traveling in my graph g, and I started looking at paths here and there. And then I assume, let's take the longest path which start with u0. It may not be unique. Okay, there could be a lot of longest paths starting at u0. That's why I said, suppose that a longest path in g with vertex u0 has length, oh okay, sorry, has length l. Okay, now let's say this path of length l. So there are two cases. Case 1 is that l is greater than or equal to k, and case 2 is that l is less than k. Okay, right? There are only two possibilities. I took a longest path starting with u0, right? So I started as u0. I traveled in my graph g, and I looked at the longest path, looked at the longest path starting at u0, and I said, okay, the length of this path is l. Okay. Now there are two possibilities. Either L is greater than or equal to K, or L is less than K. Right? If L is greater than or equal to K, I'm done. Right? Because I was looking for a path in my graph G of length at least K. So if the longest path starting at U0 has length L and L is already greater than K, then I know that I have a path of length at least K. The second possibility is, okay, someone said, no, it is possible that the path of that, sorry, the length of that path is L, but L is less than K, right? So in the first case, I'm done. In the second case, what can we say? Well, like I said, let's assume, right? This is a proof by contradiction. So let's assume my longest path starting at u0 had length L, but L was less than K, right? Now let's prove that this is not possible. Okay, so let me just draw, sorry, let me just draw a little bit, then it will be clear. So you started at u0, then let's say u2, uk, and sorry, ul, ul. Okay. So let's say the length of this path is L, right? So you started at U0, you went from U0 to U1, U1 to U2. This is a imaginary path. Okay, I'm not saying go and construct one. Assume, take a longest path, U0, U1, U2, dot, 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 up to UL. And the length of this path is L. You can see there are L edges. Now, let's assume that L is less than K. Can anyone argue here that if L is less than K, then there's something wrong? This cannot be a longest path. Um, can you use the given information in my problem and argue such that the length of this path is L and L is less than K? Then it is not possible to have a path, longest path with L less than K. Maybe I'll give you a minute to think. Uh, what does K represent? Every vertex is having degree at least K. Yes. So if you let me show you the problem again. So here K represents the smallest degree, which means that every vertex have degree at least K. Okay, I think someone answered that. Okay. Okay, so I think there is no idea, but no problem. I think this is the first relatively hard question in this session. So let's see. Okay. So let's look at this path u0, u1, u2 up to ul. What I said is that every vertex in my graph G has degree at least k, right? This is given. This is part of the problem. Every vertex has degree at least k. That means if I look at ul here, this vertex ul, the vertex ul is adjacent to at least k vertices, right? Because the minimum degree is at least k. So ul is adjacent to, now see, it could be possible that ul is adjacent to u0, it could be adjacent to u1, u2, it could be adjacent to any k vertices. But if you see, my first argument is that ul is adjacent to some vertex which is not part of this path. Okay, so claim ul is adjacent to a vertex which is not in the set u0, u1, ul minus 1. So I'm saying that there exists a vertex which is adjacent to u0, sorry, ul, which is not in this set u0, u1, u2, this. Okay, so let's see why. Why is that the case? Now, like I said, L is less than K, right? So okay, so there is one more thing. So, okay, so let me write it down. So I have assumed L is less than K implies that the size, so let's say this is my set S, U0, U1, U2, up to ul minus 1. Since L is less than k, this set has at most k vertices, right? It implies that mod S is less than or equal to k. Is that clear why mod S is less than or equal to k? It is because L is less than k, right? Okay. Now, ul is addition to k vertices. Now, clearly, there are k vertices in S, but if you see, u okay. So what I'm saying is ul is adjacent to k vertices. Since ul is already adjacent to ul minus 1, and there are at most k minus 2 vertices left, ul must have a neighbor which is not on this path, right? That means ul must have a neighbor which is not in S, not in the set S. But now this is a contradiction. Why? Because if ul has a neighbor, okay, it could be anything. It could be anything, but not on this path. Then what I can say is that this path which I drew here, ul, and let's say there is a vertex which is adjacent to ul, let's call it v. Now this is a contradiction. Why? Because in the beginning I said u0 to ul was the path with longest length starting at u0. But if I assume L is less than k, then I can construct a longer path which starts at u0 and has length more than L. So this is a contradiction, right? So this is a contradiction to our assumption that L is less than K, right? I assumed L is less than K. I took a longest path starting at U0, ending at UL. Then, since UL has K neighbors, K or more neighbors, there is a vertex V which is not on the path U0 to UL, which is adjacent to UL. So let's call it V. And with the help of that vertex V, I have constructed a longer path starting at u0, which is of length more than L. This is a contradiction to our first assumption that I took the longest path. That means what I assumed before that L is less than K was wrong. That means it implies that L is greater than or equal to K. So we have proved that every vertex, so for every vertex, there is a path starting at that vertex and it will be of length at least K, right? So wait, let me rephrase. So for every vertex u0, the longest path, a longest path starting at u0 will have length at least k. Okay, I hope this is clear. If you have any questions, please ask me. Okay, so there's a doubt, but longest path was not given in problem. It was only a path. Yes, see, what we have to show is that there is a path of length at least k. What, like you said, this is true. In the question, they said, in the question, they said path. Now, what I did is to see, in order to prove that there is a path of length at least k, I started constructing a path, right? Some imaginary path I started constructing. And I said, okay, let's start at a vertex u0. u0 could be any vertex and take a longest path, right? I can do that. I can say that go to graph G, take a vertex u0 and look at a longest path starting at u0. Now I ask you, what is the length of that path, right? Here, I took this path u0 to ul. I assumed it's the longest path. Okay. Now I asked, okay, is it possible that the length of this longest path is less than k? Here I showed in the last argument that this is not possible, that this longest path has length at least k. See, we are proving existence. We are not showing all paths have length at least k. We are saying there exists a path with length at least k. No, no, no. So here you are saying make a move from vertex A to B. It is of length less than or equal to k. Prove. No, no. See, what I'm saying is if you move from A to B, the length of that path could be L, like I assumed here. Now you have to take two cases. If L is less than, if L is greater than or equal to k, then you are done. But if I tell you, no, no, this path has length L and L is less than k, in that case, you need to have an argument to show that, no, no, the way I have assumed the path, the way I have constructed the path, it will be of length at least k, because I didn't start with any arbitrary path between any two arbitrary vertices. I took a vertex arbitrarily u0, but then I said, take a longest path starting at u0. Okay, I didn't start with arbitrary path. Okay, that is important. Not all paths of length at least k. There could be path of length 1. Just start at vertex A and take a edge and path ends, and this is a path of length 1. Right, why I'm saying I took a particular longest path and then I proved that this longest path will have length at least k. And since this longest path is in my graph G, I have a path of length at least k, right? So this is the reasoning for it. I proved that either way, you assume L is greater than or equal to k or less than k. Either way, I will show that there is a longest path of length at least k. Do we have to show any path of length less than k? Why to show that length of longest path is at least k? No, I think there's still confusion. See, what I asked in the question is, if you see, show that G has a path of length at least k. That means the question is asking me to construct a path of length at least k. So to do that, I can pick any path. I can say, okay, take shortest path, longest path, path between two vertices, path between these two vertices, this path, that path, anything. I can take any path I want,
I have to show that the path I'm constructing will be of length at
length
least
at
k,
least k,
right?
right?
And
And
this
this
is
is
not
not
true
true
if
if
you
you
take
take
arbitrary
arbitrary
path.
path.
If
If
you,
you,
like you
like you
said,
said,
start
start
at
at
a,
A,
end
end
at
at
b,
B,
and
and
this
this
is
is
a
a
path
path
of
of
length
length
k.
k.
This
This
is
is
not
not
true,
true,
right?
right?
I
I
can
can
give
give
you
you
two
two
vertices
vertices
with
with
a
A
to
to
b,
B,
and the
and the
path
path
will be
will be
of
of
length
length
less
less
than
than
k,
k,
right?
right?
Um,
Um,
but
but
in
in
order
order
to
to
construct
construct
a
a
path
path
of
of
length
length
more
more
than
than
k,
k,
I
I
hypothetically
hypothetically
started with
started
the
with the
longest
longest
path,
path,
right?
right?
So
So
if
if
you
you
have to
have to
show a
show a
path of
path
length
of
at
length
least
at
k,
least
why
k,
would
why
you
would you
start with
start with
shortest path,
shortest path,
right?
right?
Intuitively, you will
Intuitively, you will
start with the
start with the
longest path.
longest path.
If you
If you
want to
want to
construct a
construct a
path
path
of
of
longer
longer
length,
length,
why
why
would you
would you
start
start
with
with
any
any
arbitrary
arbitrary
path,
path,
this
this
path,
path,
that
that
path?
path?
Intuitively,
Intuitively,
you
you will
start
start
with the
with the
longest
longest
path,
path,
right?
right?
And
And
then
then
you
you
have
have
to
to
give
give
some
some
reasons
reasons
to
to
show
show
that
that
this
this
longest
longest
path
path
will be
will be
of
of
length
length
k
k
or
or
more.
more.
Okay.
Okay.
Uh,
Uh,
I
I
hope
hope the
the argument
argument
is
is
clear
clear
a
a
little
little
bit.
bit.
Okay.
Okay.
So
So
if
if
not,
not,
then you
then you
can
can
go
go
through the
through the
solutions I
solutions
will
I will
share
share
later.
later.
I
I
have
have
written
written
formally
formally
step
step
by
by
step.
step.
Okay,
Okay,
let me
let
go
me
to
go
the
to the
next
next
question.
question.
Uh,
Uh,
okay. So
so
let me
let me
write
write
down.
down.
Okay.
Okay,
So
so
here is
here
a
is a
question.
question.
Let
Let
me
me
explain.
explain.
So
So
you
you
have a
have a
graph
graph
G,
G,
which
which
is
is
a
a
tree.
tree.
I
I
hope
hope
all
all
of
of
you
you
remember
remember
what
what
is a
is a
tree
tree
graph.
graph.
A
A
graph
graph
is a
is a
tree
tree
if
if
a
a
graph
graph
is
is
called
called
a
a
tree
tree
graph
graph
if
if
it
it
is
is
connected
connected
and
and
there
there
are
are
no
no
cycles,
cycles,
right?
right?
So
So a tree graph is a graph which is
connected
connected
and
and
contains
contains
no
no
cycles.
cycles.
So
So
this
this
is
is
called a
called a
tree
tree
graph.
graph.
Now,
Now,
what
what
you
you
have
have
given
given
is
is
that
that
I
I
have
have
a
a
tree
tree
graph,
graph,
right?
right?
And
And
the
the
average
average
degree
degree
of
of
this
this
graph
graph
is
is
A.
A.
Okay,
Okay,
so
so
this is
this is
denoted
denoted
by
by
A.
A.
Average
Average
degree
degree
is
is
A.
A.
Then,
Then
can
can
you
you
tell
tell
me
me
how
how
many
many
vertices
vertices
are
are
there
there
in
in
the
the
tree
tree
in
in
terms
terms
of
of
A,
A,
right?
right?
I
I
hope the
hope the
question
question
is
is
clear.
clear.
So
So
the
the
average
average
degree
degree
is
is
A,
A,
and
and
the
the
question
question
is
is
how
how
many
many
vertices
vertices
are
are
there
there
in
in
the
the
tree
tree
in
in
terms
terms
of
of
A.
A.
Okay, I'll
I'll
give you
give
a
you a
couple
couple
of
of
minutes
minutes
to
to
think.
think.
Okay,
Okay,
take a
take a
minute.
minute.
Okay,
Okay,
so
so
let's
let's
see.
see.
So
So
I
I
think
think
there
there
is
is
someone
someone
in
in
the
the
chat.
chat.
Okay,
Okay,
so
so
go ahead.
Argo,
Number
number
of
of
edges
edges
equal
equal
to a
to A
minus
minus
one.
1.
Why?
Why?
I
I
never
never
said the
said the
number
number
of
of
edges
edges
equal to
equal
a
to A
minus
minus
one.
1.
I
I
said
said
the
the
average
average
degree
degree
is
is
A.
A.
V
V
minus one.
minus 1.
Yes.
Yes.
Okay.
Okay.
So I
So I
think you
think
are
you
on
are
the
on the
right
right
path.
path.
So
So
let
let
me
me
write
write
down
down
what
what
you're
you're
saying.
saying. Uh,
So
so
the
the
first
first
important
important
observation,
observation,
not
not
observation
observation
but
but
a
a
fact,
fact,
is
is
that
that
number
number
of
of
edges
edges
in
in
a
a
tree
tree
with
with
n
n
vertices
vertices
is
is
equal
equal
to
to
n
n
minus
minus
1,
1,
right?
right?
So
So
in a
in a
tree
tree
graph
graph
which
which
contains
contains
n
n
vertices, the
vertices, the
number
number
of
of
edges
edges
is
is
exactly
exactly
equal
equal
to
to
n
n
minus
minus
1.
1.
Okay.
Okay.
Now,
Now,
so
so
let's
let's
solve
solve
this.
this.
What
What
is
is
given?
given?
Average
Average
degree.
degree.
What is
What is
average
average
degree?
degree?
Sum
Sum
of
of
degrees
degrees
divided
divided
by
by
the
the
number
number
of
of
vertices.
vertices.
That
That
means,
means,
so
so
let's say
let's say
there are
there are
n
n
vertices
vertices
and I
and I
have
have
to
to
write
write
n
n
in
in
terms
terms
of
of
a.
a.
So
So
let's
let's
say
say
sum
sum
of
of
degrees.
degrees.
So
So
let's say
let's say
there are
there are
n
n
vertices
vertices
are
are
equal
equal
to
to
1
1
to
to
n
n
divided
divided
by
by
n
n
because
because
I'm
I'm
saying
saying
average
average
degree,
degree,
right?
right?
So
So
this
this
is
is
A.
A.
I
I
hope
hope
this
this
equation
equation
is
is
clear.
clear.
This
This
is
is
saying
saying
the
the
sum
sum
of
of
degrees
degrees
divided
divided
by
by
the
the
number
number
of
of
terms
terms
n.
n.
This
This
is
is
average
average
degree.
degree.
This
This
is
is
the
the
average
average
degree
degree
is
is
equal
equal
to
to
A.
A.
So
So
this
this
is
is
equation
equation
1,
1,
right?
right?
Now,
Now,
like you
like you
said,
said,
there
there
is
is
the
the
another
another
equation
equation
which
which
says
says
that
that
sum
sum
of
of
degree
degree
of
of
vertices
vertices
I is
I is
equal
equal
to
to
1
1
to
to
n
n
is
is
equal
equal
to
to
2
2
into
into
number
number
of
of
edges.
edges.
This is
This is
handshaking
handshaking
lemma.
lemma.
Now I
Now I
have
have
equation
equation
1
1
and
and
2
2
and I
and I
just
just
have to
have to
equate
equate
these
these
two
two
and
and
write
write
n
n
in
in
terms
terms
of
of
A.
A.
So
So
what
what
we
we
see?
see,
2
2
into
into
number
number
of
of
edges
edges
divided
divided
by
by
n
n
is
is
equal
equal
to
to
A.
A.
I
I
have
have
just
just
plugged
plugged
the
the
summation
summation
of
of
degree
degree
of
of
vi
vi
I equal
equal
to
to
1
1
to
to
n
n
is
is
equal
equal
to
to
whatever
whatever
is
is
there
there
in the
in the
second
second
equation,
equation,
2
2
into
into
e.
e.
Now,
Now,
the
the
number
number
of
of
edges,
edges,
like
like
he
he
said,
said,
is
is
n
n
minus
minus
1.
1.
Therefore,
Therefore,
2
2
into
into
n
n
minus
minus
1
1
is
is
equal
equal
by
by
n is
n is
equal to
equal
a
to a
because
because
number
number
of
of
edges
edges
is
is
equal
equal
to
to
n
n
minus
minus
1.
1.
Now
Now
I
I
just
just
have to
have to
write
write
n in
n in
terms of
terms of
a.
a.
So
So
2n
2n
minus
minus
2 is
2 is
equal
equal
to
to
na.
na.
Therefore,
Therefore,
2n
2n
minus
minus na
na equals
is
to
equals to
2
2
implies
implies
that
that
n
n2
minus
minus
a
a
into,
into,
so
so
n is
n is
equal
equal
to
to
2
2
divided
divided
by
by
2
2
minus
minus
a.
a.
So
So
if
if
this
this
is
is
clear,
clear,
put
put
plus
plus
1.
1.
Otherwise, you
Otherwise, you
can
can
ask
ask
me
me
questions.
questions.
Okay,
Okay,
I
I
see
see
plus
plus
ones.
ones. Okay.
For the
For the
rest
rest
of
of
you,
you,
please,
please,
if
if
you
you
have
have
doubt,
doubt,
you're
you're
free
free
to
to
ask.
ask.
Okay.
Okay.
So
So
let's
let's
move to
move
the
to the
next
next
question.
question. So let me just take the
Next
next
question.
question.
Okay.
Okay. So
Let's
let's
see.
see.
Okay.
Okay.
So
So
here
here
is the
is a
question.
question.
So
So
we
we
have
have
given a
given a
graph
graph
G.
G.
So
So
there
there
are
are
six
six
vertices
vertices
A,
A,
B,
B,
C,
C,
D,
D,
E,
E,
F.
F.
And the
And the
question
question is
is this
this
graph
graph
a
a
Hamiltonian
Hamiltonian
graph?
graph?
Okay.
Okay.
And
And
if
if
you
you
remember,
remember,
a
a
Hamiltonian
Hamiltonian
graph
graph
is a
is a
Hamiltonian
Hamiltonian
graph
graph
which
which
contains
contains
Hamiltonian
Hamiltonian
cycle.
cycle.
And
And
what is
what is
Hamiltonian
Hamiltonian
cycle?
cycle?
Hamiltonian
Hamiltonian
cycle is
cycle
any
is any
cycle of
cycle of
graph
graph
which is
which is
of
of
length
length
n.
n,
Or
or
in
in
other
other
words,
words,
oh
oh
wait,
wait,
so
so
where
where
is
is
vertex
vertex
D?
D? Oh, sorry, sorry.
Yes,
Yes,
I
I
think now
think
you
now you
can
can
see.
see.
So
So
let
let
me
me
repeat
repeat
what is
what is
Hamiltonian
Hamiltonian
cycle.
cycle.
In a
In a
graph
graph
with
with
n
n
vertices,
vertices,
any
any
cycle
cycle
with
with
length
length
n
n
is
is
a
a
Hamiltonian
Hamiltonian
cycle,
cycle,
or
or
a
a
cycle
cycle
which
which
contains
contains
all
all
the
the
vertices in
vertices in
my
my
graph
graph
is
is
called
called
a
a
Hamiltonian
Hamiltonian
cycle.
cycle.
So
So
if you
if you
have a
have a
Hamiltonian
Hamiltonian
cycle,
cycle,
you
you
call
call
it a
it a
graph.
graph.
So
So
you
you
call
call
that
that
graph
graph
Hamiltonian.
Hamiltonian.
Now
Now,
in
in
this
this
graph,
graph,
the
the
question
question
is
is
there a
there a
cycle
cycle
of
of
length
length
6?
6?
If it
If it
is
is
there,
there,
tell
tell
me
me
the
the
cycle.
cycle.
If
If
not,
not,
tell me
tell me
why
why
there
there
is
is
no
no
cycle
cycle
of
of
length
length
6.
6.
Right?
Right?
I'll
I'll
give
give
you
you
guys a
guys a
couple of
couple of
minutes.
minutes.
Um,
Um,
okay,
okay,
so
so
let
let
me
me
see.
see.
I
I
think
think
somebody
somebody
in the
in the
chat
chat
have
have
an idea.
idea.
Okay,
Okay, I
a
think a
lot of
lot of
you have
you
any
have any
idea.
idea.
Let me
Let
go
me go
one by
one by
one.
one.
So the
So the
first
first
person is
person is
saying
saying
argoel
argoel
6
6
vertices,
vertices,
sum
sum
of
of
degrees
degrees
of
of
two
two
non-adjacent
non-adjacent
vertices
vertices
is
is
greater
greater
than or
than or
equal
equal
to
to
6.
6.
So
So
Hamiltonian
Hamiltonian
graph
graph
exists.
exists.
Uh, Not
Not
true.
true.
So
So
uh,
uh,
I
I
think
think
what you
what
are
you are
saying,
saying,
I'm
I'm
not
not
sure
sure
why
why
are you
are you
saying
saying
this.
this.
But
But
see,
see,
just
just
because
because
two
two
non-adjacent
non-adjacent
vertices
vertices
have
have
degree
degree
sum
sum
n,
n,
or
or
here
here
it
it
is
is
6.
6.
So I remember that there is an Course theorem and which
Uh-huh.
states that if the sum of the degrees of the two non-adjacent vertices is greater than or equals to the number of the vertices,
Mhm.
Hmm.
then because it is not a necessary and the sufficient condition, but if it happens, then there would exist a Hamiltonian graph.
Okay,
Okay,
let
let
me
me
think
think
for a
for a
minute.
minute.
I
I
think
think
this
this
is,
is,
I'm
I'm
not
not
sure
sure
which
which
theorem
theorem
you are
you are
referring
referring
to, but
to, but
I'm
I'm
sure
sure
that
that
this is
this is
not
not
true.
true.
So let
So
me
let
give
me
you
give you
an
an
counter
counter
example.
example.
I'm
I'm
sure
sure
you
you
are
are
reading
reading
some
some
theorem.
theorem.
I
I
also
also
remember
remember
there is
there is
some
some
theorem which
theorem
says
which
that
is that
if the
if the
sum of
sum of
degrees
degrees
is
is
n,
n,
then
then
there's a
there's a
Hamiltonian
Hamiltonian
cycle,
cycle,
etc.,
etc.,
etc.
etc.
But
But
the
the
theorem
theorem
had
had
some
some
necessary
necessary
conditions,
conditions,
whatever
whatever
it
it
is, I'm
is.
not
I'm not
sure.
sure.
But
But
let
let
me
me
just
just
give you
give
an
you an
example
example
of
of
why
why
that
that
is
is
not
not
true.
true.
Um,
Um,
so
so
let's
let's
say
say
3
3
plus
plus.
let
Let
me
me
think.
think.
Um,
4,
3
3,
6.
6.
Wait,
Wait,
so
so
I'm
I'm
not
not
able to
able to
come up
come up
with an
with an
example
example
right
right
now,
now,
but
but
I
I
will
will
prove
prove
that
that
there is this
this
is
is
not
not
true
true
by
by
this
this
example
example
only.
only.
But
But
like you
like you
said,
said,
here
here
E
E
and
and
A
A
are
are
two
two
vertices,
vertices,
the
the
sum
sum
of
of
degrees
degrees
is
is
6.
6.
But I
But I
will
will
prove
prove
you
you
that
that
I will
I will
prove
prove
here
here
that
that
this is
this is
not a
not a
Hamiltonian
Hamiltonian
cycle.
cycle.
And
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 and I
also
also
tell
tell
you
you
why.
why.
Okay.
Okay.
But
But
okay, so
okay, so
let
let
me
me
just
just
see
see
the
the
other
other
uh,
uh,
comments.
comments.
So
So
Preeti
Preeti
Mandal is
Mandal is
saying
saying
it
it
is
is
not
not
a
a
Hamiltonian
Hamiltonian
graph.
graph.
Again,
Again,
this
this
is
is
correct,
correct,
but
but
I
I
need
why I need an argument to show it why it is not a Hamiltonian graph. Okay, there is one more. No, because degree of vertex is 2, not less than n by 2, that is 3 in this case. Ore is an extension of Dirac. Okay, I'm not aware of this ORE theorem, but let me prove it here that this is not true. Okay, and then I'll get back to you with maybe a different counterexample. So let's say proof. Okay, so I think does anyone have any argument of why this is not a Hamiltonian graph? Maybe something simple observation that.
Sir, may I speak?
Yes, yes, please.
Sir, for a graph to be Hamiltonian, it's necessary that all vertices are covered in one go without any vertex being repeated, and the starting and the ending vertex should be same. Like if we go from A, B, C, D, E, F, then we should go back to A. Then only it is a Hamiltonian graph. But in this example, if we start moving from A, then at most we can cover four vertices, not more than four vertices. Suppose we move from A, then we go to D. From there, we can go to either F or E. So the rest of the two vertices, like B and C, we cannot traverse them in one go. So it is not a Hamiltonian graph.
Okay, so this is a good observation that if I start at A, I will always be left out with couple of vertices. Uh, but see, I think this is one more important aspect I have to explain it to you is that when you are against such questions, these ideas or these observations may not work in the exam in the sense that, like you said, your observation is correct. If you start at A, you go to D, F, let's say E, you will miss out couple of vertices, but you can observe such a thing because the graph is relatively small here. Instead of 6, if I have given you probably 12 vertices, then it would have been hard for you to observe such a situation, right? So
Yes.
I need some, an elegant way to just skip past a lot of explanation and just like a quick argument as to why this is not Hamiltonian. Okay, so let me maybe explain. So I think this is one more. I don't know if it is a theorem, but let me just say. So let me write down. Okay, so here is an observation. I will, if you haven't seen this before, I will prove it to you. Just one line argument, and then you can quickly skip past through explanation using this argument. So what it says is the following. So let's say you have a graph G. Okay, what you decided to do is decides to delete some vertices S, right? So S is here denoting some subset of vertices. So let me write S is subset of vertices. It could be anything. So what this is saying that if G is Hamiltonian, then the number of connected components I will get after I delete vertices in S from G, the number of connected components would be at most the size of S. Let me give you an example of what I'm saying. So let's say, okay, so here is a graph G. Okay, now if I pick S is equal to, let's say, B and C. Okay, I have picked a set. You can, and this is for all S that is subset of G. Uh, can anyone tell me how many connected components are there once I delete B and C from the graph?
Three.
Sorry.
3, 3.
Um, no, right. So if
No,
I
two,
delete
sir. It will be two. Two.
two, two, yeah, I think so. You counted B and C also. So because this is just this much. Once I delete B and E, not vertices. Okay, I think you some of you are have some confusion. I'm talking about number of connected components. And here there are only two connected components. There are three vertices, but with only two connected components. Right? So the number of connected components here is two. Okay. I hope that is clear. Now, what we are saying is that if the graph is Hamiltonian and you decided to delete any set S of vertices, then the number of connected components should be at most the size of S. Okay. I'll prove this in a minute, but before that, in this graph G, can you find a set S such that this inequality is not true? So let me circle it. So this is not true. So can you find a set S in this graph G such that if you delete S from my graph G, the number of connected components is more than size of S? Okay, I'll give you a minute to think. Uh,
So if we remove what it says D and F, so basically we are removing only two vertices, and in that case we will get I think three components.
okay,
So
let's see. Just a minute. So you're deleting D and E.
D and F.
Oh, sorry, D and F. And you are claiming that I will be left with three connected components.
Yes.
Uh, is that true? Can you see once again? I can see only two components. One is A and the other one is B, E, and C. So so if you take, let me write down
So if we
S.
delete E,
Yes. Okay. This is right. So I think you said E. So let me write down and make it okay. So if you take S is equal to set E, okay, the set contains only one element E. And if you delete E, how would the graph look like? You will have one connected component which is B and C, and then there is one connected component A, B, and F, right? So you deleted one vertex. So the size of S is 1, but the number of connected components you've got is sorry, not greater than or equal to 2. That means this statement in the red box I have written here is not true, that the connected components in G minus S are somehow more than the size of S. That means the graph is not Hamiltonian. I will prove this statement in a minute, but can you all see that once you delete one vertex, in particular E, then you are getting two components? Please put +1 if you can see this. Okay, I think at least some of you can see. Okay, so now let me take a step back and prove this small argument, and then you can use it in. See, most of the time you will see only couple of kind of two, three kinds of argument for such questions, for this Hamiltonian kind of questions, and this is probably the one which will be in your exam or somewhere. So let me explain why this is true. And there is one more problem which will cover the other argument. So trust me, if you understand these two questions correctly, given any graph, if it is not Hamiltonian in exam, you will able to answer it. Okay, so let me prove that why is that true. So let's say there is a graph which is Hamiltonian. What does that mean? There is a graph which contains a cycle which is Hamiltonian, or in other words, a cycle with n vertices or all the vertices. So let's say here is a graph which contains all the cycles. Let's say v1, v2, dot 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 up to vn. Okay, so let's say this is my graph G, and this is a Hamiltonian graph. And there could be other edges that I have not drew. So there could be this edge, and maybe some other edges. Like this could be anything, but at least the cycle is there, right? v1, v2, dot 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 up to vn. The cycle is there because I have assumed that the graph is Hamiltonian, right? Now, if you see, if you have a cycle of length n which contains n vertices, and let's say you delete. Okay, so let me draw here nicely. Let me explain through an example, nice example. Okay, here is a cycle of length 6. If you remove two vertices, what is the maximum number of connected components you can get? Can anyone tell me? So this is a graph with 6 vertices, and it contains a cycle of length 6. It contains a cycle of length 6. That means it is a Hamiltonian graph. Now, if I delete, let's say only one vertex, how many connected components can be there?
5.
Once.
One.
One, I think somebody said 5. Again, let me repeat. What I'm talking about is not number of vertices. I'm talking about number of connected components. So if I delete this vertex, that means delete this edge. Then let me just delete this. So if you see in the, if I delete this, I'm left with only one connected component, right? Now, let me draw this back. If you observe, since this is a cycle, if I remove one vertex, I'll be left with at most one connected component. If I delete two, let's say I decided to delete two. So let's say I decided to delete these two.
Then 2 connected components will be there.
Yes, at most two. Because, yes, you're right. So if instead of this, if I decided to delete this one, then again I'm left with, sorry, let me just quickly draw this. So if I delete these two red vertices, then I am left with one component only. That means if you see, if you have a cycle, this is an observation. That's why this is not a lemma or theorem. If you delete some number of vertices, so let's say if you delete k number of vertices and the graph is Hamiltonian, you will be left with at most L number of connected components because there is a cycle. And since this is a Hamiltonian graph, you can have more edges in your graph G. This is true. But I know these edges there or not there, I at least have this cycle, right? And as long as I have this cycle, I can put a lower bound, sorry, not lower bound, upper bound on the number of connected components. That means if I delete L vertices, any L vertices, the number of connected components will be at most L. Okay. And in this example, in the top example, there was a vertex, there was a set S, which was of size 1, such that if I deleted it, then it contained two connected components. That means it is called a cut vertex. But anyways, that's not the point. The point is that if there's a vertex whose deletion is giving two components, then it is clearly not a Hamiltonian graph. Okay. Okay, so I hope this part is clear. Is this a necessary condition or a sufficient? This is a necessary condition. So if you see, this is a if and then statement, right? If G is Hamiltonian, something must be true. That means this is necessary, right? So I hope this answers your question. This is necessary, not sufficient. If this condition is true, then it's just necessary, not sufficient. Okay. Okay, so now I'll give you the other problem and then you will see the other argument. Let me just question. Just a minute, let me. Okay, let me write it down. Okay. So I will explain. Let me explain the question. So I have given a graph G, which is denoted by K subscript M comma N. I'll tell you what it is. And the question is it Hamiltonian? Where M plus N is odd. So let me explain what is K M comma N. So K M comma N is a complete bipartite graph with M vertices in one part and N vertices in other. Okay, so what is Km comma n? Km comma n denotes a complete bipartite graph with M vertices on one side and N vertices on the other, such that the vertices on left side are adjacent to the vertices on right side. All of them are adjacent to each other from left to right. So let me give an example. So let's say K3 comma 4. What is K3 comma 4? So I will draw three vertices on left side and four vertices on right side, right? So this is left, this is right. And complete means this oh sorry, this vertex is adjacent to all of them. This vertex is adjacent to all of them. This vertex is adjacent to all of them, right? Complete bipartite. Bipartite means there is a left side and right side here, like I've discussed. And all the edges are going from left to right or right to left. There is no edge here. If you see this, these three vertices doesn't have any edge. These four vertices doesn't have any edge. And complete bipartite means all the vertices on left are adjacent to all the vertices on right. Okay. I hope the graph Km comma n is clear. What kind of graph it denotes. If you don't understand, look at this question K3 comma 4. Sorry, this example K3 comma 4. Um, and think, is Km comma n Hamiltonian when m plus n is odd?
No, sir.
Just a second. Uh, so you are saying no. Okay, why is it not possible?
A bipartite graph must have even number of vertices, and it should be so that it can be partitioned into two. That is the theorem I remember.
So your reasoning, I think, is almost right. So first condition. So okay, how many of you remember what is a bipartite graph? Can anyone give me a quick definition?
A bipartite graph is a graph wherein the set of vertices can be separated into two disjoint sets which have equal number of vertices.
No, this is not true. So let me give an example of bipartite graph, which is where like what you said is not true. So here is an example of bipartite graph. The left side contains two vertices. So left, right. The left side contains two vertices and the right hand side contains only one. And this is still a bipartite graph. So let me define what is a bipartite graph. I will give you two definitions. So first one is maybe this one. So you can partition the vertices into two parts. For now, let me call it left and right just for the imagination. So let's say you can partition the vertices into left and right such that the edges of that graph can only go from left to right or right to left. It is not possible that there is an edge between two left vertices or there is an edge between two right vertices. Right? So if you see here, there is no edge between these two left vertices. So you can have a lot of vertices here like this. And this could be anything. But if you see, this is a bipartite graph because the vertices on the left do not have any edge. And similarly, the vertices on right do not have any edge. All the edge in some sense are crossing from left to right or right to left. Okay, this is one definition. And I'm sure you have seen this in your class, another definition. So a graph is bipartite if and only if, so this is a necessary and sufficient condition. if and only if the graph does not contain any odd cycle. Okay, so this is one more definition. I hope you have seen this in your class, or if not, I think you will see it. I'm not sure if you have already seen it, but let me explain it. So let's say you have given a graph G, and somebody told you that there is no cycle of odd length, right? I'm hoping that you know what is the length of the cycle, right? So this is a cycle of length 3, this is a cycle of length 4, right? So the number of edges in your cycle are is the length of the cycle. If somebody told you that here is my graph G and it doesn't contain any odd cycle, then it is a bipartite graph, which means that you can partition it into two parts, left and right, um, such that there is no edge between any two left vertices and there is no edge between any two right vertices. Okay, so use this definition, go back and solve this problem. Anyone? Uh, okay, so let me explain. So here is a graph that I have given k m comma n. Okay, so can anyone tell me how many vertices are there in k m comma n graph?
M plus n
M
vertices.
plus sense.
Yes, correct. So there are m plus n vertices. Now, if you see, the graph is Hamiltonian if and only if there's a cycle which is equal to the number of vertices. The length should be the number of vertices. That means this graph km comma n will be Hamiltonian if there is a cycle of length m plus n. Right? This is pretty straightforward. This is by definition that if this is Hamiltonian, then there must be a cycle of length m plus n. I know this km comma n graph is bipartite. That means there is no odd cycle. And if m plus n is odd, which implies that there is no cycle of length m plus n as well, right? So let me write, since there are no cycles of odd length, implies there does not exist any cycle of length m plus n, which implies that there does not exist any Hamiltonian cycle. Right? So I have given a graph G and it is a bipartite graph. It means it doesn't contain any odd cycle or a cycle of odd length. Now, a Hamiltonian graph is a graph which contains a cycle whose length is equal to number of vertices. So this graph would have been Hamiltonian if and only if there is a cycle of length m plus n. But the question told me that m plus n is odd. And now, since the graph is bipartite, there cannot be a cycle of odd length. In particular, there cannot be cycle of length m plus n. So this is not possible. Uh, I hope this is clear.
Yes, sir.
Okay. Okay, so now let me write down the next question.
What can we say about if m plus n is even, then whether it will be Hamiltonian or not?
Okay, that's a good question. So let me actually write it down here. So what if m plus n is even? So does anyone have any idea what if m plus n is even? Will that graph be?
Yes, sir, that can be a Hamiltonian cycle because it will not contain cycle of odd length.
No, no. See, just because it doesn't contain a cycle of odd length, that only means it contains a cycle of even length. But to be Hamiltonian, not only it should have even cycle, it should have a cycle of length m plus n, right? So
Maybe
given
Hamiltonian or may not be Hamiltonian, sir.
yes, so can you? So can anyone give me? So you're right. The graph could be Hamiltonian or may not be Hamiltonian. So can anyone tell me when the graph would be Hamiltonian? Um,
When m is equal to n.
yes, yes. So I'll explain why. So when m is equal to n, so if m is equal to n, then m plus n will be even. So that is not necessary. So when m is equal to n, then k m comma n is Hamiltonian. Okay, and m is greater than or equal to 2. Right, so if m is equal to 1 and n is equal to 1, then clearly this is just an edge, so there is no Hamiltonian cycle. So I have to assume that m is greater than or equal to 2. And then if this is given, then you can easily construct a Hamiltonian cycle, because you just have to start with the left vertex, jump to right, take with right, go here, left, left, right. Since there are equal number of vertices and every vertex is the addition to every vertex, you can always jump from a vertex here to here, and eventually you will see that you will end up on the, if you start with the left vertex, you will end up with right vertex by covering all the edges, sorry, all the vertices, and eventually take the edge which goes from the right last vertex to the first vertex. Okay, this is just an observation. I mean, I don't have to prove it, so I hope this is clear. Okay, now let me give you some more interesting problem. uh, okay, so I think this is a bit probably long answer, so let me write it down. Sorry. So if G is a simple graph with three vertices and E edges such that E is greater than E minus E equals 2, then G is always connected. Okay, so let me explain you the question and then you can think for a minute. So I have given a simple graph G. Okay, it contains, so let me actually use a different notation which will be simpler, which contains n vertices and m edges. This will be simple. M edges, and the number of edges, which is m, is at least n minus 1 choose 2. N minus 1 choose 2. Then the graph is connected. You have to show that the graph is connected. Right? A connected graph is a graph with only one connected component, right? Which is the entire graph G. So you can think for a minute. I think this is relatively, I mean, it is simple, but I think the explanation is a bit long. So you can think for a minute.
Sir,
Yes.
so in previous question, why we take a condition m greater than or equal to 2, sir?
So because, so let's say m is equal to 1 and n is equal to 1, right? So let me draw here. So let me draw here. So let's say m is equal to 1 and n is equal to 1. So this is k 1 comma 1. So can you see there is no cycle of length 2 here? See, when is the graph Hamiltonian? If there's a cycle of length n, where n is the number of vertices. In this graph, n is 2. I mean, not n is 2, n is 1. The total number of vertices, let's say v of g, is equal to 2. But clearly, there is no cycle of length 2. I mean, there is no such thing as cycle of length 2 in simple graphs. In a simple graph, you will always have cycle of length at least 3. So that's why I said m should be at least 2.
Thank you, sir.
Okay, yes. Okay, so I don't see any comment till now. Uh, okay, so let me ask you a simple question. So, in a graph, in a simple graph with n vertices, what is the maximum number of edges possible? Right? So, you have a graph G which contains n vertices. So, how many edges can be there? Maximum. Right. So, somebody wrote n into n minus 1 by 2, which is correct. So, if you have a graph with n vertices, then maximum number of edges possible is n choose 2, right? So how do you construct an edge? You choose two vertices, so n choose 2 is the number of edges, which is equal to n into n minus 1 by 2. Now here I have given n minus 1 choose 2, which they are saying if n choose 2, then the graph is connected for sure, right? Every vertex is adjacent to everything, so clearly the graph is connected. We are proving a relatively stronger statement, which is that there are if the number of edges is n minus 1 choose 2, the graph is still connected. I mean, more than n minus 1 choose 2. Okay, so let's prove this. This is a relatively, I mean, just a couple of steps, but let me write it down. So, claim 1, if the number of edges is more than n minus 1 choose 2, then the graph contains a vertex with degree at least n minus 2. Okay, so this is a step 1. In while proving this is a step 1. So I will prove it to you that if you have given a graph G with n vertices and the number of edges is m and m is at least n minus 1, not at least, more than n minus 1 choose 2, then there will always exist a vertex whose degree is at least n minus 2, right? So let's prove it. So can anyone give me any idea of how what I can use here to prove this claim 1? Okay, so let me prove it to you. I think we don't have much time. So we'll use the handshaking lemma. Handshaking lemma. Okay, what is handshaking lemma? Summation of degree of vertices 1 to n is 2 into number of edges, right? Let me add some edges. Okay, so what I have given? I have given that number of edges is at least n minus 1 choose 2, right? This is given to me, and this is handshaking lemma. So what I can say is that summation of degree of vertices from I is equal to 1 to n is equal to 2 into n minus 1 choose 2.
Okay.
Okay. Now, sorry, this is greater than. I have to, this is greater than, right? This is from equation 1. So from 1 and let's say this is 2 and 2. If you combine these two, then you get this inequality. Now, what I have to show is that there is a vertex with degree at least n minus 2. So I will prove this by contradiction. So let's say for the sake of contradiction, assume that degree of every vertex, degree of vi, is less than or equal to n minus 3 for all I. So again, so I'm proving this by contradiction, which means that I'm assuming something which is opposite to what I have to show, right? So I am assuming all the vertices have degree n minus 3 or less than or equal to n minus 3. So if you see this I equal to 1 to n, now since every integer in this sum is less than or equal to n minus 3, then total will be at most n to n minus 3. Can you see this? So let me say this is 3. Right? Every integer here is less than n minus 3, and I'm summing n terms, where each term in that summation is at most n minus 3. It will imply that the total sum is at most n into n minus 3. Okay. Now let's look at, let's say this is 3 and this is 4. It implies degree of vi, the summation I is equal to 1 to n, is greater than 2 into n minus 1 choose 2 and at most n into n minus 3. So let's see this term and this term. N into n minus 3 should be greater than, actually strictly greater than 2 into n minus 1 choose 2. So let me simplify a bit. It implies that n minus 1 into n minus 2 divided by 2, n into n minus 3, which means n into n minus 3 is greater than n minus 1 into n minus 2. So let's see. So this means that n square minus 3n is greater than n square minus 3n plus 2. It means if you take this, then it implies 0 is greater than 2. So this is a contradiction. So let me recall what I did. So I had to show that there is a vertex in my graph G of degree at least n minus 2. So here, for the sake of contradiction, in this star step, I assume that all vertices have degree at most n minus 3, right? I'm assuming this to show that something will go wrong if we assume this. That means the sum of degrees is at most n into n minus 3 because each term is at most n minus 3. Now from equation 3 here and equation 4, I get this inequality. If you remove the middle term here, then I get this term. N into n minus 3 is greater than 2 into n minus 1 choose 2. So if you simplify this, you get a contradiction. It implies 0 is greater than 2. But since we all know 0 is less than 2, it implies that there is a vertex with degree at least n minus 2. Right? Until this point, does anyone have any questions? Please ask. Okay, I see one plus 1. Okay, so I don't see any questions. And okay, so that means there's a vertex here which is adjacent to n minus 2 vertices. So I'll say again, the vertex could be anything. Let me denote it by u, and it is adjacent to v1, v2, v3, v4 up to vn minus 2. And let's say this is v0. So actually, let me just do this simply. So let's say this is v1 and it is adjacent to v2 V2, V3, V4, V5, Vn minus 1.
Okay.
Okay.
So
So
what I
what I
have
have
shown
shown
is
is
that
that
there is
there's
a
a
vertex
vertex
V1,
V1
which
which
is
is
adjacent
adjacent
to
to
n
n
minus
minus
2
2
vertices.
vertices.
So
So
I'm
I'm
just
just
denoting
denoting
it
it
by
by
V2,
V2,
V3,
V3,
V4,
V4,
V5,
V5,
Vn
Vn
minus
minus
1.
1.
Now,
Now,
I
I
know
know
that
that
um,
um,
still I
still, I
have
have
not
not
proved
proved
that the
that the
graph
graph
is
is
connected
connected
because
because
I
I
am
am
left
left
with
with
one
one
vertex
vertex
which
which
is
is
Vn,
Vn,
right?
right?
So the
So the
argument
argument
is
is
not
not
done
done
yet,
yet,
right?
right?
Now,
Now,
what
what
I
I
know,
know,
if
if
you
you
look
look
at
at
the this
this
graph,
graph,
the
the
graph
graph
induced
induced
by
by
the
the
vertices
vertices
in
in
this
this
red
red
color.
color.
So
So
if you
if you
look
look
at
at
the
the
graph
graph
induced
induced
by,
by,
I
I
hope
hope
induced
induced
graph
graph
concept
concept
is
is
clear.
clear.
So
So
if you
if you
look
look
at the
at the
graph
graph
induced
induced
by
by
this
this
n
n
minus
minus
1
1
vertices,
vertices,
which are
which are
basically in
basically in
this
this
red
red
square,
square,
how
how
many
many
edges
edges
can be
can be
there?
there? Oh, wait, this is closed.
Right. So
Right. So
what
what
I'm
I'm
asking
asking
you
you
is
is this
red
red
part,
part,
this
this
red
red
circle,
circle,
contains
contains
n
n
minus
minus
1
1
vertices.
vertices.
So
So
I
I
asked
asked
you
you
at
at
some
some
point
point
how
how
many
many
edges
edges
can be
can be
there
there
in a
in a
graph
graph
with
with
n
n
vertices,
vertices,
and
and
someone
someone
so said
said
n
n
choose
choose
2.
2.
But
But
now
now,
if
if
I
I
have
have
only
only
n
n
minus
minus
1
1
vertices,
vertices,
so
so
let's
let's
say the
say the
graph
graph
was
was
disconnected
disconnected
and
and
there
there
was
was
no
no
edge.
edge.
So
So
this
this
is
is
component
component
maybe
maybe
2
2
and
and
this
this
is
is
component
component
1,
1,
and the
and the
graph
graph
is
is
disconnected.
disconnected.
But
But
this is
this is
not
not
done
done
yet.
yet.
Why?
Why?
Because
Because
I'll
I'll
explain.
explain.
Uh,
Uh,
so
so
how
how
many
many
edges
edges
can
can
be
be
there
there
in a
in a
graph
graph
with
with
n
n
minus
minus
1
1
vertices?
vertices?
N
N
minus
minus
1
1
choose
choose
2,
2,
right?
right?
n minus 1 choose to.
So
So
the
the
number
number
of
of
vertices,
vertices,
oh
oh
sorry,
sorry, number of edges
in the
in the
red
red
part
part
is
is
at
at
most
most
n
n
minus
minus
1
1
choose
choose
2,
2,
right?
right?
Okay.
Okay.
Now,
Now,
if
if
you
you
see
see
the
the
question,
question,
what
what
it
it
said
said
is
is
that
that
the
the
total
total
number
number
of
of
edges,
edges,
which
which
is
is
m,
m,
is
is
strictly
strictly
greater
greater
than
than
n
n
minus
minus
1
1
choose
choose
2.
2. So let me just write in this in corner. M is greater than n minus 1 choose 2.
That
That
means
means
that
that
if
if
you
you
decided
decided
to
to
put
put
all the
all the
edges in
edges
the
in the
red
red
part,
part,
this is
this is
still
still
not
not
enough
enough
because I
because I
have
have
more
more
edges,
edges,
right?
right?
So
So
if I
if I
had
had
n
n
minus
minus
1
1
choose
choose
2
2
edges
edges
in
in
my
my
graph
graph
sheet,
sheet,
then the
then the
graph
graph
would
would
have
have
been
been
disconnected
disconnected
because
because
I
I
could
could
have
have
constructed a
constructed a
complete
complete
graph
graph
with
with
n
n
minus
minus
1
1
vertices
vertices
and
and
left
left
out
out
one
one
vertex
vertex
vn.
vn.
But
But
I
I
know
know
that
that
the
the
number
number
of
of
edges
edges
is
is
at
at
least
least
n
n
minus
minus
1
1
choose
choose
2
2
plus
plus
1,
1,
right?
right?
What
What
it
it
implies
implies
is
is
that
that
there
there
is
is
an
an
edge
edge
coming
coming
from
from
this
this
red
red
part
part
and
and
going to
going to
vn.
vn.
So
So
there is
there
an
is an
edge
edge
which
which
is
is
going
going
from
from
p
p
to
to
red
red
part.
part.
Now
Now,
if
if
you
you
observe,
observe,
it
it
doesn't
doesn't
really
really
matter
matter
whether
whether
that
that
edge is
edge is
adjacent to
adjacent to
v3
V3
or
or
v1,
V1,
could
could
be
be
anything.
anything.
This is
This is
already a
already a
connected
connected
graph,
graph,
right?
right?
So
So
that's why
that's
the
why the
graph is
graph is
connected.
connected.
So
So
I
I
hope
hope
this is
this is
clear.
clear.
So
So
I
I
said
said
there is
there
a
is a
vertex
vertex
with
with
n
n
minus
minus 2
uh, degree.
degree.
Then I
Then I
said,
said,
okay,
okay,
I'll
I'll
put
put
one
one
connected
connected
component
component
where
where
I
I
have
have
this
this
n
n
minus
minus
1
1
vertices.
vertices.
With
With
v1,
V1,
it is
it is
adjacent to
adjacent
n
to n
minus
minus
vertices.
vertices.
But
But
then it
then it
says,
says,
okay,
okay, I'm
I'm
still
still left
left
with
with
one
one
vertex.
vertex.
Now,
Now,
I
I
argued
argued
that
that
since the
since the
graph
graph
contains
contains
more
more
than
than
n
n
minus
minus
1
1
choose
choose
2
2
edges,
edges,
there
there
is
is
an
an
edge
edge
which
which
comes
comes
out of
out of
vn
Vn
and
and
goes to
goes to
some
some
vertex
vertex
2 to
to
some
some
vertex
vertex
in
in
component
component
1.
1.
I
I
have
have
this integer
integer
element,
element,
whether
whether
it is
it is
adjacent to
adjacent to
v3,
V3,
v4,
V4,
v5,
V5,
vn
Vn
minus 1,
minus 1,
v1,
V1,
anything.
anything.
The
The
graph is
graph is
still
still
connected,
connected,
right?
right?
Because
Because
I
I
mean,
mean,
I
I hope this is easy to see. So that's why the graph is connected, right? So if you understand, put +1, or else please ask me questions.
So, what is the difference between an Eulerian circuit and an Eulerian graph?
Um,
Um,
Eulerian
Eulerian
circuit
circuit
and
and
Eulerian
Eulerian
graph.
graph.
Okay,
Okay,
so
so
okay, so I
I
hope
hope
you
you
have
have 2 minutes.
2 minutes.
I'll
I'll
just
just quickly
quickly
do
do
one
one
question
question
on
on
Eulerian
Eulerian
graph,
graph,
and
and
then
then
it
it
will
will
be
be
clear.
clear.
Okay.
Okay.
So
So
let
let
me
me
just do
just do
one
one
question.
question.
It's just
Just
one
one
line
line
question,
question,
so
so
it
it
will
will
not
not
take
take
more
more
than
than
2
2
minutes.
minutes.
Let
Let
me
me
write
write
it
it
down,
down,
and
and
then
then
I
I
will
will
explain
explain
you
you
what
what
you
you
asked.
asked.
Does
Does
there
there
exist
exist
does there
does there
exist
exist
a
a simple Eulerian graph on 6 vertices and 7 edges. Okay. Okay, so this is the question. So let me explain this question. The question is asking the following: does there exist a graph, a simple graph? A simple graph is graph with no parallel edges, no, what is it? Loops. So I have to construct a simple graph which is Eulerian. Now let me explain what is Eulerian graph. So a graph is called Eulerian graph if you can, what is it called? You can transverse through every edge exactly once. Let me give you an example, then it will be clear. So this is my graph G. What do I mean by traversing? It will be clear. So let me just say, let's say this is A, B, C, D, E. So Eulerian circuit is basically the following. So you can start at A. Okay, so let me say you started at A. You traversed an edge. So you went to B. Then you went from B to C. You went from C to E. You went from E to D. Then you went from D to C. So let's say A, B, C, E, D. Then you went from D to C again and C to A. So this sequence is a Eulerian circuit. Why? Because I have started with a vertex A, or you can start with any vertex, and I have traversed through this graph in such a way that the first vertex is also the last vertex, as you can see, and every edge is traversed exactly once. We are not allowed to repeat any edges. On top of that, every edge must be there in my this sequence. So you can see A, B, B, C, C, E, D, D, C, and C, A. So how many edges are there? 1, 2, 3, 4, 5, 6. How many edges are there in the graph G? 1, 2, 3, 4, 5, 6. That means this is an Eulerian circuit. And what is Eulerian graph? Anything which contains Eulerian circuit. Or it also, okay, I don't know the other terminology, but if it contains a Eulerian circuit, then this is called the Eulerian graph. Okay, I hope the definition is clear. Now, can you construct a simple graph, a simple Eulerian graph with 6 vertices and 7 edges? I'll give you a minute and then I'll give you the answer. Okay, there's a question. Do we have Euler's graphs and Hamiltonian graphs for directed graphs as well, or something analogous? Mhm. I'm sure that the definition of Eulerian circuit exactly lifts to directed graph. So regardless of the, so those of you who don't know what a directed graph is, you can put direction on the edges, and the definition of Eulerian circuit can be carried forward to directed graphs as well. So you can, wait, where is my pen? So if you have, so let me, I don't think this is covered in class, but let me just write down. So if this is A B, sorry, A B B C C E E D, then D C and C A. So the definition of Eulerian circuit carries forward to the directed graphs exactly. You can traverse. Now, if there is an edge from C to A, then in the while traversing the graph, you cannot jump from A to C, right? But you can take forward the definition of Eulerian circuit to directed graphs as well.
Sir, it is not possible to draw a simple Eulerian graph with 6 vertices and 7 edges.
Okay, why not? Explain.
Because the number of edges is more than the number of vertices. So there will be at least one loop. Even if we go to draw the graph, there will be at least one loop.
No. So let me make something clear. When you have a cycle, then you are not allowed to repeat edges, right? If you have a cycle, then you are not allowed to repeat edges, right? But in the Eulerian circuit, I mean, in the Eulerian circuit, you are also not allowed to repeat edges, but you are allowed to repeat vertices. So there's a subtle difference, right? When I say cycle, the definition of cycle is that you traverse the graph such that you will get some sequence of vertices such that first and last vertex is same. The adjacent vertices are, I mean, the consecutive vertices are adjacent. And lastly, you are not allowed to repeat any edge or any vertex. Now, when I go to Eulerian circuit, I'm allowed to repeat vertices, right? So this is a subtle difference. I'm allowed to repeat Eulerian vertices in my Eulerian graph or Eulerian, what you call trail. To make it Eulerian circuit, you just have to make two vertices equal. So cycle and let's say Eulerian trail, vertices and edges are not allowed to repeat except the first and last, except the first vertex and last vertex. In the Eulerian trail, edges are appearing exactly once. So here also repetition of edges is not allowed exactly once, but you can repeat vertices as much as you want. So this is, there is no restriction on repetition of number of vertices. Okay. Now, can you construct a Eulerian graph on 6 vertices and 7 edges? Okay, so there's a comment. All vertices should be of even degree for Euler circuit. Yes, so this is a theorem which you have seen, I'm sure, in your class, that a graph is Eulerian if and only if the degree of every vertex is even. And those of you who are asking for directed graph, this is, I'm just telling you out of interest. Okay, this is not in the probably in your course. In a directed graph, if for every vertex in degree and out degree is equal for every vertex, then there's a Eulerian tour in the directed graphs as well. In degree and out degrees, how many edges are going in, how many edges are going out. If that is equal for every vertex, then it will be a Eulerian graph in directed graphs. Okay. But anyways, let's come back to undirected graphs. Okay, can you give me an example? Uh, can anyone give me an example? This is true. I'll give you an example which is very simple, but I want you to, one of you to maybe uh, give me an example. Okay, maybe I think we are already over time, so let me give an example.
Example of what?
Example of an Eulerian graph which is simple and it contains 6 vertices and 7 edges.
Okay, okay.
So let me give it to you. I think we are already 10 minutes over the time. So here is an what is called 6 vertices, 3, 4, 5, 6. V1, V2, V3, V4, V5, V6. And then 1, 2, 3, 4, 5. That's a 6 and 7. So now let me tell you what is the Eulerian tour here. I start at V1, then I go to V2, then V3, V4, V5, V6, V3, and back to V1. I think all of you can see that this is an Eulerian tour because I have traversed every edge. There are 7 edges and all of them are appearing here exactly once. And second, vertices are allowed to repeat in Eulerian tour or trails. This is only for cycles where or paths the vertices are not allowed to repeat, because you can see V3 is repeating here more than once. And V1 is there, which is true for cycles as well. But this is a simple observation. You can see there are 6 vertices and 7 edges. Right? So is this clear? If it is clear, then put +1 or else ask me question.
Okay,
Okay,
so
so
I
I
see
see
few
few
plus
plus
ones.
ones.
Okay,
Okay,
so
so
we
we
are
are
already
already
over
over
time,
time,
so
so
I
I
will
will
have
have
to
to
stop
stop
the
the
class.
class.
So
So
I
I
will
will
share
share
with
with
you
you
the,
the,
I
I
think
think
not
not
not I
I
will
will
share,
share,
but
but
somehow
somehow
the
the
link
link
will
will
be
be
shared
shared
with
with
you
you
of
of
this
this
recording.
recording.
Uh,
Sir, there is a problem. I have registered for this course as well as Basic Calculus 1
Uh-huh.
by some professor of IIT Madras.
Uh-huh.
And the doubt session for tomorrow is the same time, 5 to 7, for
Mhm.
graph theory as well as Basic Calculus 1. So, how would I manage both?
okay,
Okay,
so
so
let
let
me
me
say
say
this.
this.
So
So
first
first
of
of
all,
all,
uh,
um,
the
the
sessions
sessions
of
of
the
the
session
session
of
of
today
today
and the
and the
session
session
of
of
tomorrow
tomorrow
is
is
independent.
independent.
That
That
is
is
first.
first.
I'm
I'm
not
not
sure
sure
who
who
will
will
take
take
the
the
tomorrow's
tomorrow's
class.
class.
Probably
Probably
some
some
different
different
TA
TA
will
will
take
take
tomorrow's
tomorrow's
class,
class,
and it
and
will
it
be
will be
conducted,
conducted,
I
I
think, in
think,
the
in the
same
same
manner.
manner.
Second,
Second,
both
both
the
the
recordings
recordings
of
of
today
today
and
and
tomorrow's
tomorrow's
session
session
will be
will be
available
available
to
to
you.
you.
And
And
if
if
you
you
have
have
doubt
doubt
in
in
some
some
particular
particular
recording
recording
while
while
you
you
are
are
reading it
reading it
or
or
watching
watching
it,
it,
you
you
can
can
ask
ask
in the
in the
same
same
in the
in the
next
next
class.
class.
Okay,
Okay,
but
but
I
I
don't
Thank
don't
you,
think
think
I
sir.
I
can
can
do
do
anything
anything
about
about
the
the
overlapping.
overlapping.
Okay.
Okay.
Okay,
Okay,
so I
so I
think
think
I
I
don't
don't
know
know
who
who
will
will
take
take
the
the
tomorrow's
tomorrow's
class,
class,
but
but
uh, anyways.
anyways. Okay,
So
so
I
I
hope
hope
everything
everything
is
is
clear.
clear.
And
And
okay,
okay,
so
so
goodbye
goodbye
then.
then.
I'll
I'll
stop
stop
the
the
meeting.
meeting.
Oh my God.